Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss centrifugal pumps, suction pressure limits cavitation and net positive suction head. The single most common operational problem in a process plant is loss of suction pressure to a centrifugal pump. If the suction pressure is too low, the discharge pressure and the discharge flow become erratically low. The suction pressure, while low, remains comparatively steady. Cavitation and net positive suction head. The problem described above is called cavitation. A pump that is operating in a cavitation mode may also, but often does not, produce a sound similar to shaking a bucket full of nuts and bolts. A cavitating motor-driven pump always draws an erratically low amperage flow. This is consistent with the erratically low flow rate. You should be cautious when a pump completely loses flow. It runs smooth, steady, and quiet. Its discharge pressure is stable. Its discharge flow is also stable and steady, a steady zero. This is not cavitation. The pump impeller is just spinning, to no particular purpose, in the empty impeller case. Causes of cavitation. Let us assume liquid flows from an 8-inch line into the suction of a centrifugal pump. The liquid enters the pump's impeller through a circular opening, called the eye of the impeller, in the center of the impeller. Let us assume that this eye has a diameter of 2 inches. The velocity of the liquid increases by a factor of 16, that is, 8 inches divided by 2 inches squared. The kinetic energy of the liquid increases by a factor of 264, that is, 16 squared. But where does this large increase in kinetic energy come from? Answer is from the pressure, or feet of head, of the liquid itself. The conversion of the pump's suction pressure to velocity in the eye of the impeller is called the required net positive suction head, NPSH. As the flow control valve on the discharge of the pump shown in picture is opened, the velocity of liquid in the eye of the impeller goes up. More of the pump's suction pressure, or feet of head, is converted to velocity, or kinetic energy. This means that the required NPSH of a pump increase as the volumetric flow through the pump increases. The units of NPSH are feet of liquid head. The required NPSH of a pump is due primarily to the conversion of feet of head to velocity in the eye of the impeller. The available NPSH to a pump has the following definition. Physical pressure pump at suction minus vapor pressure of liquid at pump suction. To express the available NPSH in feet, measure the pump suction pressure and add the barometric pressure, 14.67 psia at sea level. Look up, on a vapor pressure chart, the vapor pressure of the liquid pumped, at the measured pump suction temperature, in psia. Multiply the difference between the two above pressures by 2.31 feet, for water. Divide by the specific gravity at flowing conditions of the liquid, 1.00 for water, 0.85 for diesel, 0.50 for propane at the pump suction temperature. Note that the pump suction pressure is the pressure downstream of the pump suction screen, and not a pressure read from a control panel screen. When the required NPSH of a pump equals the NPSH available to the pump will cavitate or slip. Cavitation illustrated. Let us see what cavitation means in reference to the pump shown in picture. The liquid shown in the vessel is presumed to be in equilibrium with the vapor leaving the drum. This means that the liquid is at its bubble point pressure and the vapor is at its dew point temperature. The vapor pressure of the liquid is then 24.7 psia or 10 psig plus 14.7 psia of atmospheric pressure. The physical pressure at the suction of the pump is measured at 29.7 psia, 15 psig plus 14.7 psia of atmospheric pressure. Then the physical pressure at the suction of the pump of 29.7 psia minus the vapor pressure of the liquid at the suction of the pump of 24.7 psia is 5 psia. This will be the NPSH available to the pump after we convert from psia to feet of liquid head. The specific gravity of the liquid being pumped, as shown in picture, is 0.58 specific gravity. To convert from psia to feet of liquid head, we have 5 psia times 2.31 divided by 0.58 is equal to 20 feet of head. The 20 feet matches the level of liquid in the drum above the suction line of the pump, shown in picture, and equals the available NPSH to the pump. The required NPSH of the pump may be read from picture, regardless of the specific gravity of the liquid being pumped. It shows that at 250 GPM, the required NPSH of 20 feet will equal the available NPSH of 20 feet. Therefore, at a flow rate of 250 GPM, the pump will cavitate. This calculation has neglected frictional losses in the suction line and nozzle, which should be subtracted from the available NPSH. Let's now assume that we wish to pump 300 GPM, not 250 GPM. If we open the flow control valve shown in picture, the flow will momentarily increase. But within a few seconds, the flow will become erratically low as the pump begins to cavitate. The problem is that, according to picture, we require an additional 6 feet of NPSH to increase the flow from 250 to 300 GPM. One way of getting this extra suction pressure, or NPSH, is to raise the liquid level in the drum. For a liquid of 0.58 specific gravity, with every 4 feet we raise the level in the drum, the suction pressure will increase by 1 psi, and the available NPSH will increase by 4 feet. But unfortunately, the drum shown in picture is already almost full. Suppose we increase the pressure by partly closing the back pressure control valve. This will quickly increase the pressure in the drum from 10 to 15 psig. The pressure at the suction of the pump will also increase, from 15 to 20 psig. However, will this provide more NPSH to the pump? Answer is no. Unfortunately, it is not only the pressure of the liquid at the pump that changes. The composition of the liquid will also be altered. As the pressure in the drum increases, additional lighter components dissolve in the liquid. The composition of the liquid then becomes lighter. The vapor pressure of the liquid will also increase by 5 psi. This must happen because the liquid in the drum, which is in equilibrium with the vapor, is at its bubble point pressure. Again, the available NPSH is the physical pressure at the suction of the pump minus the vapor pressure of the liquid at the suction of the pump. If both pressures increase by 5 psi, the net gain in NPSH is 0. Let us try again. Suppose we decrease the temperature of the drum, shown in picture, from 140 to 110 degrees Fahrenheit. This will also cool the liquid flowing into the suction of the pump by 30 degrees Fahrenheit. Will this colder liquid then provide more NPSH to the pump by suppressing the flashing of the liquid flowing into the pump's impeller? Answer is no. Unfortunately, it is not only the temperature of the liquid that changes. The composition of the liquid has also been altered. As the temperature in the drum decreases, additional lighter components dissolve in the liquid. The composition of the liquid becomes lighter. The liquid will now boil, not at 140 degrees Fahrenheit, but at 110 degrees Fahrenheit. This must happen because the liquid in the drum, which is in equilibrium with the vapor, is at its bubble point temperature, which is now a cooler 110 degrees Fahrenheit. Let's try one more time. Suppose we tear off the insulation on the suction line and on the pump case and then spray cool water on the bare line. The temperature of the liquid in the drum, which is at 140 degrees Fahrenheit, cools as it flows into the pump. By the time the liquid reaches the eye of impeller, it is cooled to 135 degrees Fahrenheit. Will this slightly colder liquid provide more NPSH to the pump? Answer is yes. But why? Well, the liquid is cooled by 5 degrees Fahrenheit after it leaves the drum. The cooled liquid is not in equilibrium with the vapor in the drum. It has been subcooled by 5 degrees Fahrenheit. This means that the bubble point liquid has been cooled without altering its composition. The vapor pressure of the liquid has been reduced. As can be seen in picture, subcooling this particular liquid by 5 degrees Fahrenheit reduces its vapor pressure by about 2 psi. As the specific gravity of the liquid is 0.58, this is equivalent to an increase in the NPSH by 8 feet. Once again, our objective is to increase the flow from 250 to 300 GPM. Picture tells us that the required NPSH increases from 20 to 26 feet. However, when we subcool the liquid by 5 degrees Fahrenheit, the available NPSH increases from 20 to 28 feet. As the available NPSH now exceeds the required NPSH by 2 feet, the flow can be increased without risk of pump cavitation. Starting NPSH requirement. The required NPSH read from the manufacturer's pump curve is called the running NPSH. However, when a pump is put online, there is an additional type of NPSH requirement. This is called the starting NPSH. The initial velocity of the liquid in the suction of the pump is 0. After the pump is up and running, the velocity of the liquid in the suction of the pump might be 6 feet per second. This means that the liquid in the suction line has to be accelerated, which requires energy. This energy does not come from the pump. It must come from the liquid in the suction line itself. The only source of energy the liquid has is its pressure. This means that the pressure of the liquid is converted into kinetic energy. The kinetic energy accelerates the liquid from 0 to 6 feet per second. This results in a temporary loss of pressure at the suction of the pump. This temporary loss of pressure is called the starting NPSH requirement. The more quickly the operator opens the discharge valve of a pump, the more rapidly the liquid accelerates in the suction line. This increases the starting NPSH required. The longer the suction line and the larger the diameter of the line, the more mass has to be accelerated. This also increases the starting NPSH required. If the sum of the frictional loss in the suction line plus the running NPSH plus the starting NPSH equals the available NPSH, then the pump will cavitate on startup. The experienced design engineer always allows for the starting NPSH requirement when determining the elevation of a vessel. It is hard to say whether to allow an extra 2 feet or an extra 10 feet. It depends on the size of the suction line and how careful the operators are likely to be when starting the pump. But if the designer forgets this factor, then the plant operators are sure to notice the omission when the pump slips during startup. Watch my lecture on centrifugal pumps fundamentals for detailed calculations for starting NPSH. A hunting story. At a refinery, operators had to start up the pump shown in picture. This was a new, flashed crude oil pump. It had never been run before. The refinery operators reported that the pump always cavitated on startup. They had raised the liquid level in the drum to within a few inches of the inlet nozzle. A higher level would cause entrainment of the black crude oil into the vapor outlet. The operators had then started the motor driving the pump. Next, they very slowly opened the discharge valve. Regardless of their efforts, the pump cavitated so badly that it could not be put in service. Some pumps are like that. The design engineer just never allowed any extra liquid elevation for the starting NPSH. But what could he do? You see, guys, here is the problem. The pump needs to be started on urgent basis. Temporary solution. Increase in NPSH. This pump is presumed to run fine once it is running. The available NPSH is such that it exceeds the running NPSH. So how can he provide a temporary increase in the available NPSH to satisfy the temporary starting NPSH requirement? Answer is suddenly increase the pressure in the drum by partly closing the back pressure control valve shown in picture. This will instantly increase the pressure at the suction of the pump. It is true, as we said before, that raising the pressure in a drum does not increase the available NPSH, assuming that the vapor and liquid are at equilibrium. The idea of equilibrium assumes that the vapor is at its dew point and the liquid is at its bubble point. As soon as the drum pressure is raised, the vapor composition in the drum is altered. The vapor composition becomes lighter. The vapor, though, is still at its dew point. As soon as the drum pressure is raised, the liquid composition in the drum is altered. The liquid composition at the vapor-liquid interface becomes lighter. The liquid formed at the vapor-liquid interface is still at its bubble point. When this lighter liquid works its way down to the suction of the pump, the beneficial effect achieved by raising the pressure in the drum is gone. The available steady-state NPSH will be exactly what it was before the drum pressure was raised. But this will take time. If the residence time of the liquid in the drum is 10 minutes, then it will take 10 minutes for the lighter liquid to reach the suction of the pump. During this 10-minute interval, the liquid flowing into the pump is the older, heavier composition. If he raises the pressure in the drum suddenly by 5 psi, this instantly supplies about 20 feet of additional available NPSH, but only for a period of less than 10 minutes. During this period, he can crack open the pump discharge valve, push the motor start button, and then slowly accelerate the liquid in the suction line by slowly opening the discharge valve. If he can do all this before the lighter liquid formed at the vapor-liquid interface in the drum reaches the eye of the pump's impeller, then he can start up the pump. Thus, even though we lack the extra available NPSH to satisfy the pump's starting NPSH requirement, he could still start the pump. Why some pumps cavitate? Pumps cavitate for 3 reasons. They lack sufficient available NPSH to satisfy the conversion of pressure to velocity in the eye of the impeller running NPSH. They lack sufficient available NPSH to satisfy the conversion of pressure to acceleration in the suction line as the pump is starting NPSH. They lack sufficient available NPSH to overcome the frictional losses in the suction piping and the drain or draw nozzle. It is positively my experience that the most common reason for pumps cavitation is partial plugging of draw nozzles. This problem is illustrated in picture. This is the side draw-off from a fractionator. Slowly opening the pump's discharge control valve increases flow up to a point. Beyond this point, the pump's discharge pressure and discharge flow become erratically low. It is obvious, then, that the pump is cavitating. The fluid being pumped is hot water. At the desired flow rate of 110 GPM, the manufacturer's pump curve shows that the pump requires 14 feet of NPSH. The elevation difference between the draw-off nozzle and the suction of the pump is shown on picture as 46 feet. We really ought to have plenty of running NPSH. But apparently, we do not. If I reduce the flow of water by just 10% down to 100 GPM, the cavitation stops. I now put a pressure gauge on the suction of the pump. Assuming that the suction line is full of 46 feet of water, what suction pressure would I expect? Answer: 46 feet divided by 2.3 feet per psi plus 30 psig equals 50 psig. The 2.3 feet per psi factor assumes that the specific gravity of water is 1.00. But the observed pressure is not 50 psig. It is only 47 psig. I am missing 3 psig or 7 feet of liquid. 50 psig minus 47 psig times 2.3 feet per psi equals 7 feet. The most likely explanation for this head loss of 7 feet is frictional loss in the suction line. This reduces the available NPSH from 46 to 39 feet. But this is still a lot more available NPSH than the 14 feet of required NPSH needed to pump 110 GPM. If I now open the discharge flow control valve sufficient to increase the flow from 100 to 110 GPM, or by 10%, this will increase the frictional loss in the suction piping by about 21%, or about 0.5 psi. Delta P varies with square flow. But this is not what I observe. The suction pressure in picture slips from 47 to 36 psig, at which point the pump begins to cavitate. What is happening? How could just a 10% increase in flow cause such a large increase in the suction line delta P? What has happened to the lost 11 psi, that is, 47 psig minus 36 psig of suction pressure? The boiling point pressure of the water is equal to 30 psig, the pressure in the tower shown in picture. That is, we can assume that the water draw-off is at its bubble point pressure. At 36 psig pump suction pressure, the available NPSH is then 36 psig minus 30 psig times 2.3 is equal to 14 feet. This matches the required NPSH at a flow of 110 GPM, so the pump cavitates. But it still seems as if I am missing at least half of the 46 feet of liquid head to the pump. Where is it? Well, dear gentlemen, it no longer exists. Picture illustrates the true situation. Let's say we are pumping 110 GPM from the pump discharge. But only 109 GPM can drain through the draw-off nozzle. We would then slowly lower the water level in the suction line. The water level would creep down, as would the pump's suction pressure. When the water level in the suction line dropped to 14 feet, the pump would cavitate or slip. The flow rate from the pump would drop, and the water level in the suction line to the pump would partially refill. The pump's NPSH requirement would then be temporarily satisfied. Normal pump operation would be restored, but only for a moment. Of course, it may simply be that the draw-off nozzle is undersized. To determine whether this is the case, calculate the velocity v through the nozzle in feet per second. Delta H equals 0.34 v square, where delta H is the hydraulic head in inches of liquid required to push 110 GPM of liquid through the draw-off nozzle. In this case, delta H is found to be 9 inches of water. Apparently, there is twice as much pressure lost through the nozzle than there should be. This indicates that the draw-off nozzle must be partly plugged. The 0.34 coefficient shown is the conversion of potential energy to acceleration, which includes a reasonable allowance for turbulence and friction. The theoretical coefficient is about 0.18, which only includes acceleration. In my designs, I use 0.34 for nozzle exit losses, which my experience has shown represents what I actually observe in the field, plus a small safety factor. Vortex breaker. Many draw-off nozzles, especially those in the bottom of vessels, plug because of the presence of vortex breakers. Many designers routinely add complex vortex breakers to prevent cavitation in pumps. But vortex breakers are needed only in nozzles operating with high velocities and low liquid levels. Corrosion products, debris, and products of chemical degradation can more easily foul and restrict nozzles equipped with vortex breakers. Lack of available NPSH may also be caused by high frictional loss in the suction piping. If this is the case, a small reduction in flow will not noticeably increase the pressure at the suction of the pump. A properly designed suction line to a centrifugal pump should have a frictional head loss of only a few feet of liquid. However, having a large diameter suction line and a relatively small draw-off nozzle usually will lead to excessive loss of available NPSH. Marginal cavitation. On many occasions, I've noticed that large, high-head pumps with a low suction pressure do not cavitate in the normal way. They do not develop an erratic discharge pressure and an erratic flow. When these pumps are marginally short of NPSH, both flow and discharge pressure remain steady. What does happen is that the pump discharge pressure falls by 50%, 100 to 150 psi. That is, a reduction in pump suction pressure of 1 psi causes a fall in pump discharge pressure of 100 psi, raising the level in the vessel from which the pump is taking flow by just 2 feet dramatically increases the pump's discharge pressure. It seems as if the pump's performance jumps from an inferior performance curve to its normal performance curve as shown in picture. Pump suction under vacuum. Liquids in storage tanks are almost always subcooled. This is so because otherwise the ambient vapor losses from the tank's vent would be excessive. This creates the potential for a negative pump suction pressure. For example, the pump shown in picture is suffering from a partially plugged inline suction filter. The positive pressure to the filter of 5 psig is due to the 15 feet head of liquid in the tank. The filter delta P is 12 psi. Hence, the pressure at the suction of the pump is -7 psig. Since atmospheric pressure happens to be 15 psia on this particular day, the pressure at the suction of the pump is 8 psia. The liquid being pumped is methanol, which has a vapor pressure, at the pumping temperature of 100 degrees Fahrenheit, of 3 psi. The physical pressure at the suction of the pump, 8 psia, minus the vapor pressure of the liquid at the suction of the pump, 3 psi, equals 5 psi. To convert the 5 psi to feet of head, 5 psi times 2.3 divided by 0.77, specific gravity, equals 15 feet. The 0.77 is the density of methanol. The 15 feet of head is the available NPSH to this pump. Does this mean that pumps may have a substantial amount of available NPSH even when their suction pressure is under a partial vacuum? Yes, if we are pumping a subcooled liquid. But this is quite common, because the liquid stored in an ordinary atmospheric pressure storage tank is almost always well below its boiling point, that is, the liquid is subcooled. Sump pumps. The most common pump used is the sump pump shown in picture. The vast majority of the pumps in the world are of this type. They are the sort of pumps used to pump water out of shallow wells and from irrigation ditches. We use thousands of these pumps to push rainwater over the levees and into the mighty river. Some pumps can draw water up from levels as much as 30 feet below the pump's suction. But do such pumps require NPSH? Absolutely. All centrifugal pumps have some NPSH requirements. What, then, is the available NPSH to the sump pump shown in picture? The physical pressure at the suction of the pump is the pressure at point A. The pump was lifting water from an oily water sump. The water level in the sump was 9 feet below the center line of the pump's inlet. 9 feet of water is equal to 4 psi, that is, 9 divided by 2.31. This means that the pressure at point A was -4 psig. Atmospheric pressure on this particular day was 14 psia. The absolute pressure at the suction of the pump was then 14 psia minus 4 psi equals 10 psia. The vapor pressure of water at the 140 degrees Fahrenheit pumping temperature is 3 psia. The suction pressure at the pump minus the vapor pressure of water at the suction of the pump is then 7 psi, that is, 10 psia minus 3 psi. The suction line itself was a rather rough, old cast iron pipe, with a frictional loss of 2 psi. This frictional loss must be subtracted from the 7 ps I just calculated. This leaves 5 psi available for us to convert to feet. 5 psi times 2.31 feet per psi equals 11.5 feet. This 11.5 feet is the NPSH available to the pump. The pump itself requires only 6 feet of NPSH to pump 1200 GPM of water. Hence, even though the pump's suction is 9 feet above the water in the sump, the available NPSH is twice the required NPSH. A pump that is lifting very cold water, with a very low vapor pressure, through a smooth, low frictional loss suction line, with a very small NPSH requirement, operating at sea level, where atmospheric pressures are high, can lift water to its suction by perhaps 30 feet. The pump shown in picture can lift 1200 GPM of water by only 15 feet. When the water level in the sump drops to 15 feet below the center line of the pump's impeller, the pump will cavitate. Where, then, does the available NPSH to a sump pump really come from? It comes from atmospheric pressure. Atmospheric pressure at sea level is equivalent to 14.7 psia times 2.31 feet of water per psi equals 34 feet of water. In theory, this is the greatest height that water can be lifted from a well by a surface pump. In practice, this maximum lift height is 25 to 30 feet. Of course, water is pumped from borehole wells hundreds of feet deep. But this is done by submersible pumps, which are let down into the well. Loss of prime. The only real difference between a sump pump and an ordinary centrifugal pump is that the sump pump is more difficult to prime than the ordinary pump. To prime an ordinary pump, we simply crack open the vent valve on top of the pump's case. The pressure of the liquid in the suction line pushes out the gas or air trapped in the pump case to the atmosphere or to the plant's flare line header. Once the pump case is full of liquid, it is primed and ready to go. The problem with priming the pump shown in picture is that the water needed to fill the pump's case, that is, to prime the pump, is below the pump itself. Certainly, there are self-priming pumps. These pumps are designed to compress very, very small volumes of air, and to produce very, very small discharge pressures with the air. The circulation pump on my swimming pool is of this type. After running 15 minutes or so, it draws through itself a few cubic feet of air before it can pick up suction. Most high-head, large volume pumps must be primed with an external source of water. In picture, this is done by connecting a water hose to valve A and opening valve B. Air is pushed out of the pump case by the pressure of water in the hose. When the pump is in operation, the suction pressure of the pump is -4 psig. This negative pressure creates a potential problem. Air may be drawn into the suction of the pump through leaks in the suction line. One especially vulnerable area is the packing gland around the valve stem of the pump suction valve. Another potential area of air in leakage is around the pump's mechanical seal. Air drawn into either area will cause the pump to cavitate and lose its prime. The flow through the pump will then be lost. Playing a water hose over a leaking valve stem packing gland or over a bad seal can temporarily restore the pump to normal operation. Even better, spread grease on the leaking valve stem. Self-flushed pumps. The pump shown in picture is an illustration of an installation in a refinery. The difficulty with this pump was that it would lose its prime after being shut down for just a few moments. What is the problem? Answer is there is an error in the design of this pump. The error is that this is a self-flushed pump. The mechanical seals on centrifugal pumps require a lubricant or seal flush material to keep the seal faces from touching and rubbing. In most pumps, this seal flush fluid comes from the discharge of the pump itself. Such pumps are called self-flushed pumps. When a self-flushed pump is running, the space between the seal faces is filled with the seal flush fluid. When the pump is shut down, the space between the seal faces is filled with the fluid in the suction of the pump. However, if the pressure at the suction of the pump is below atmospheric pressure, then air is drawn through the seal faces and into the suction of the pump. This air displaces the water in the pump's case and, with time, causes the pump to lose its prime. To fix this problem in refinery, engineer connected an external source of seal flush water to the pump from a nearby wash water station. Pumps that have subatmospheric suction pressures and that are not in continuous service should not be self-flushed pumps. They should have an external source of seal flush material connected to the mechanical seal. With the external source of seal flush, the pump no longer lost its prime when shut down. However, he then noticed an interesting phenomenon. The pump would continue to run for about an hour after it stopped raining. It produced a discharge pressure of about 100 psig. Then, quite suddenly, the discharge pressure would drop to 70 psig and the amp load on the motor driver would slip from 20 to 14 amps for its last few minutes of operation. The cause of this odd behavior is that the water level in the sump had dropped. A layer of oil with a specific gravity of 0.70 had been drawn into the suction of the pump. The feet of head developed by the pump had not changed. But a pump's discharge pressure is proportional to delta P is proportional to density times feet of head. As the specific gravity of the oil had dropped by 30%, so had the pump discharge pressure. The amperage load on the motor driver is also proportional to the weight of liquid pumped, which also changes with the specific gravity of the liquid. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.